Good morning, everyone. I'm Yashka Khatri, and today I'll be talking on the topic mealy and mealy machines in Automata Theory and Compiler Design. As we know that finite automata is the simplest model of computation and it also has very limited memory. It consists of a set of initial and final states where we can transition from one initial state to another and back to the previous state as well. Finite automata are basically classified on the basis of their outputs. Finite automata, that is, finite automata with output, they are classified as Moore machine and Mealy machine. And finite automata without output, which are classified as ZFA, NFA, and epsilon NFA. Now we'll be talking about Moore machine. Moore machine is a finite state machine where the output depends only on the current state. It is defined by a set of six tuples. Here, Q represents finite set of states. That is Q0, Q1 up to Qn number of states we can have in our Moore machine. And sigma stands for the finite set of input alphabet. That is the input string which will be given by the user. It can be either A, B, C, D or 0 or 1 as well. Same goes for finite set of output alphabets. It can be A, B or 0 and 1 and ranging from any alphabets to number representations. And for the transition function, it defines the relationship between the finite set of states and finite set of output alphabets. That is, since in Moore machine, our output depends only on the current state, so we'll represent it as this. And lambda stands for the output function, and Q0 is the initial state. Now we'll get a more good understanding of the Moore machine by taking an example. Here we have to design a Moore machine to calculate the ones complement of a binary number. Here our input tuple is 0 and 1, that is our finite set of alphabets, and our output are also finite set of alphabets, that is same as the input. So for ones complement, the logic goes like this. If we have 0, we'll change it to 1, and if we have 1, we'll change it to 0. So let's get a better understanding of it by taking as an example. If we have the input this, that is, if we have first we read the string 1, then it go for 1 it goes to initial state only Q0 and gives the output as 0. 1 again 0. Then for 0 it transitions to another state Q1 and gives the output as 1 here. And next is 1 1. Again it will go back to its initial state 1 and give the output as 0. And for another one, it gives the output as 0. And for the 0, for the next 0, I'll go to Q1 and it will give the output as 1. So here we can see as for every 1, there is a 0, and for every 0, there is a respective 1 in the as from output to from input to output. Hence, we'll take it by another example also, that is 1101. So for 1, again, we go back to the initial state and our output is 0. Again 1, 3 zeros. Then when we have the next 0, we'll transition to the next state, that is Q1, and we'll get the output as 1 as we are having 0 in the input string. And for the 1, we go back to the initial state and we get the output as 0. So here, as we can see, transition table for this particular Moore machine as well. In the present state, when the input is 0, it goes to state Q1, and when the output is 0, when the input is 1, it goes to state Q0, that is itself only. So at Q0, at each state, present state, the output is 0, devoid of the next state. And same goes for Q1 also. Hence, it clarifies that in Moore machine, our output depends on the current state. In mealy machine, We have the opposite. Our output depends upon the current state as well as the input given. Here also we have five tuples, that is Q, that is finite set of states, again Q0, Q1, Q2 up to Qn, and sigma, finite set of input alphabets as well. Delta, finite set of output alphabets, 0 or 1, A, B, C, D. Transition function. Here the transition function is different from Moore machine as this has both dependencies, that is current state as well as the input given. So we'll write it like this: finite set of states and input alphabet gives the relation to the finite set of output alphabets. And lambda is our output function and Q0 is the initial state. We'll get a more clearer understanding of this by taking an example again. So in mealy machine, we have to design a mealy machine. When 01 is encountered, it prints A. So for the input 01, this is our input tuple. So first, the basic rule to design a mealy machine is, first we have to consider the smallest strings possible it can accept. So basically our accepted set of strings can be 01, the smallest, and not accepted is 10. Then again, accepted strings can be 101, 001, 1001, as they are all ending in 01. But these strings do not end in 01, so they are not accepted. Let's get a better understanding by taking an input string. For for example, I'll take the string 1101011. For 1, we are at A only, so it gives the output as B. And for once again 1, same. For the 0, we go back to the next state, that is B, and it gives the output B. So now we have 0. So it goes back to the same initial state as B and gives the output as B. Now for 1, it goes back to it goes to C and gives the output as A. That is this. And for 0, it goes back to B and gives the output as B. Then we are here at B. Now we have 1. So for 1, we'll go back to C again and it gives the output as A. And finally, for the last string, that is 1B, it gives the output as B. So here we can see that for an instance of 0, as it encountered the string 0 and 1, it gave the output A. And once again it encountered it 0, 1, it gave the output as A. So as we had to design a mealy machine which gives the output as A whenever 0, 1 is encountered, so there are two occurrences, so two A's are present. And here, since there is no occurrence of 0, 1, so it has given the output as B only. Now we'll look at the transition table for this. In the present state A, if A has to move to the next state with input 0, it gives the output B. And from A to A with input 1, it gives the output B. Similarly, for B and C, it does the respective outputs. And one thing here that is different from Moole machine, again, we see is that here input is depending upon the next state as well as the output. The outputs are different at each state. So we'll relate Moore and Meere machines to now the real life examples. For the Moore machine, our first example is elevator control system. As we have seen in an elevator that we can move between different floors when we press the button. So once we reach a particular floor, the door opens and it only depends upon our current floor state and not on the other floor states. That is, we have many requests lined up for other floors, but we only go to the first respective floor. So here, it only depends upon our current input, not on the next number of inputs that are given. So, elevator control system is a example of Moore machine. Next example can be automatic washing machine. Washing machine has different cycles. That is, it can wash, rinse, are clothes. So for the output, only depends upon the current cycle, that is, what state the machine is in, for the wash state or the rinse state or the spin. So once a state starts, it cannot change midway due to new inputs. Hence, for a washing machine, when it is washing the clothes, it cannot change its states midway, and hence it is an example of Moore machine. For mealy machine, we'll take the example as traffic light, as traffic light has sensors and it can detect vehicles at an intersection. So if it is red, the all the cars stop, and if the traffic light is green, all the cars can go. So here the output depends upon two things, that is the current state, red, yellow or green light, and the sensor input, whether the vehicles are detected or not. So it is an example of a melee machine. And another example is vending machine, which accepts coins and checks the correct amount has been inserted. So if an invalid coin is, suppose we have to purchase an item of 10 rupees and we are inserting only 5 rupees. So that item can't be taken out from the vending machine. So here the output depends upon two things: the total money collected and the user input, that is the coin inserted. So it is also an example of melee machine. Thank you.